Hello, good people. I hope you are good. So, on today's presentation, we'll be focusing on ways of treating wastewater with nanofibers. Firstly, we have to know what nanofibers are. So, nanofibers are one-dimensional fiber materials having dimension in the nanometer range of 10 to the power of -9 nanometer. Synthesis of nanofibers. There are two basic methods used to prepare carbon nanofibers, which are electrospinning and chemical vapor deposition. Electrospinning is a mechanical and electrical technique of producing ultrafine fibers in the submicron and nanometer diameter range using high voltage. So, the process involves the electrodynamic process, where a liquid is slowly pumped into the syringe. Then the droplet is formed at the spiral tip and high voltage, and high voltage is needed for Taylor cone formation. Once the droplet surface tension is overcome by high voltage, the fiber elongation and solvent evaporate to form solid fibers. Chemical vapor deposition. Chemical vapor deposition is a process in which the substrate is exposed to one or more volatile precursors, which react or decompose on the substrate surface to produce the desired thin film deposit. So it is basically a technique where a solid material is deposited from a vapor by some chemical reaction occurring in the vicinity of a normally heated substrate surface. It is used in semiconductors industry to produce thin films. The whole process occurs in a chamber at a temperature of 500 to 1000 degrees Celsius. The surface is driven due to thermal energy, and the reaction process occurs in the presence of gas with inert atmosphere. Water treatment using nanofibers. Due to the exceptional characteristics which resulted from nanoscale size, such as improved catalysis and adsorption properties as well as high reactivity, nanomaterials have been the subject of active research and development worldwide in recent years. Numerous studies have shown that nanomaterials can effectively remove various pollutants in water and thus have been successfully applied in water and wastewater treatment. Major nanofibers water treatment application. We have heavy metals, CEC removal, which CEC stands for contaminants of emerging concern, and desalination. Heavy metals. Nanofiber adsorbent are attractive options for heavy metal and metal ion removal. The nanofiber is incorporated with certain functional groups to make it more selective towards the heavy metal. The selective nanofiber based on the target metal ion characteristics, allowing adjustable base diameter, porosity, and hydrophobicity, as well as quicker additive integration and microstructure creation. The basic mechanism that nanofibers follow to remove heavy metals from wastewater is adsorption, accompanied by ion exchange, photocatalytic process, electrostatic interaction between metal ions, diffusion dialysis, and metal organic framework crystal or polymers. Adsorption is viewed as a transfer progression of mass in which heavy metals from wastewater get deposited on nanofibers by either physical adsorption or chemical adsorption. In physical adsorption, chemical reactions take place on the adsorbent surface. Firstly, heavy metals in the wastewater transfer to the surface of nanofibers and vice versa. Then from the exterior surface of nanofibers, heavy metals diffuse into the nanofibers, which is the rate limiting step. Finally, chemical or physical interaction occur between heavy metals and nanofibers. The significant functional groups of the nanofiber surface selectively adsorbs the heavy metal, and equilibrium is achieved at a constant concentration of adsorbed heavy metal in wastewater. CEC removal. Removal of submicron contaminants is achieved by the electroadhesion and ion exchange. Filter is based on the mineral Pseudohymide. Each gram of alumina fiber has a surface area greater than 500 sq meters. The active fibers are 2 nanometers in diameter and approximately 250 nanometers in length. The crystal structure of the mineral creates a natural electrokinetic potential of aluminum 3+ on the surface of the fiber. It is not an electrostatic charge that can be dissipated by alcohol immersion. Charge potential maintains integrity between pH of 5 to 9.5 in polar liquids. The available hydroxyl group in each fiber will also exchange protons with many electropositive colloids to retain them through a form of ion exchange. Still on CEC removal, the crystal structure allows extremely high surface area and a large number of active sites for submicron contamination removal. The pore size of the media is engineered such that the charge field covers the entire void of every pore. There are approximately 400 layers of these pores in the thickness of the media that contamination passes through during filtration, creating a tortuous path. The charge field removes the negatively charged submicron particles while the larger particles are captured with the fiber structure of the media. The nanofiber captures small particles that are not captured by conventional mechanical filters. The nanofiber filter captures organic and microbial macromolecules. It removes bacteria and viruses, mean pore size of 1.25 microns, cartridge pressure drop of less than 0.1 bar, unique benefits which are high flow rates, low pressure drop at submicron retention, and each layer has nano-alumina, powdered activated carbon, antimicrobial silver, and approximately 400 layers of charged fibers. Reduction levels. Pathogenic contamination has been considered as a significant worldwide water quality concern. The bacterial pathogens in drinking water supplies cause one of the biggest threats to the public health. So nanofiber membranes, because of their high surface area to involve ratio, nano-sized pores, and high porosity, they increase the reduction levels of virus and bacteria in water. Desalination. Desalination is the removal of excess salt or other minerals from water to obtain fresh water that is good for consumption or irrigation. Nanotechnology, specifically nanofiber membrane, is a relatively new method of producing membrane for water treatment and desalination. Membrane techniques are used in different ways such as reverse osmosis, forward osmosis, membrane distillation, and nanofiltration. In conclusion, safe drinking water has long been a major concern around the world. Over the years, new technologies have been developed to meet increasing demand and required drinking water standards. In this regard, nanofibers have added a new dimension to the problem of water purification. These nanofibers provide beneficial properties such as high surface area, strength, and optimized pore size. Electrospinning is an easier and more convenient way to make nanofibers. This provides a convenient way to adjust the pore size of nanofibers. So this is where we obtained all the information in this presentation. Thank you for watching. Hopefully you learned something. Please don't forget to like, subscribe, and comment. Bye.